Hello and welcome to our course on drone surveying. In today's lecture, we are going to focus on the extraction of digital terrain models from drone mounted laser scanning data or a drone LiDAR. As we have previously defined, digital terrain model or DTM is a mathematical representation, that is a model of the bare earth surface in digital form. DTMs, along with digital surface model or DSM, they both are essential in several application areas. For example, flood or disaster risk monitoring and management, infrastructure planning, environmental protection, and nowadays they have become a fundamental data set within geographic information systems. So let's look at a motivating scenario first. In a hilly region, terrain mapping over a large and inaccessible area is required for natural disaster studies. You can think of Uttarakhand, you can think of Sikkim as an example. Furthermore, power transmission line mapping is also needed to inspect cables damaged by recent disasters. DSM and DTM from a drone camera acquired images are therefore generated to answer and study these. However, due to forest canopy, DTM cannot be generated accurately with photogrammetry, and the transmission line cables were also not visible in the DSM. So, what can we do? How can we see under the forest canopy to measure the terrain? So, LiDAR mounted on drones, they can measure the terrain and segregate fine features. As a technology, LiDAR itself has been around for several decades, but only in recent years it has become available in size and power, feasible to be carried on drones. And advances in lightweight drone LiDAR categories, they're happening very quickly. So as a quick recap of what LiDAR and what is a drone LiDAR. LiDAR stands for light detection and ranging, and it collects precise data in the form of 3D point clouds by emitting high powered laser beam to measure distant targets. So drones provide high degree of flexibility for LiDAR sampling with flight patterns similar to those of traditional airborne platform or traditional airborne LiDAR scanning. Although drones have an advantage that they can fly closer to the ground and they have shorter and tightly spaced flight lines that provide close range, multi-angular and consistent views of target structure. So common types of drone LiDAR are topographic LiDAR, which map topography using near infrared lasers, and also bathymetric LiDAR, which maps sea floor and riverbed elevation. And in the bathymetric LiDAR, it has concentric infrared and green lasers. So while the infrared laser is reflected from the land or from the water surface itself, the green wavelength can proceed into the water and it gets reflected from the bottom of water body. This makes it possible to capture both water surface as well as the waterbed bathymetry simultaneously. So in today's lecture, we will focus on topographic LiDAR only. So if we look at the components of drone LiDAR survey, then there are primarily four components. There is a laser scanner which is attached on the drone, and this laser scanner transmits the pulse which gets reflected back from the object on the ground. So the laser scanner measures the time of travel for that pulse and also measures at what angle the laser scanner emitted that pulse. There is also inertial measurement unit which measures the roll, pitch and yaw. There is also GNSS antenna on top of the drone which measures the position of GNSS in WGS 84 coordinate system. There is also a GNSS station on the ground which acts as a base to correct the trajectory of the GNSS observation on the drone. Then the core of the collection process involves simultaneous recording of precisely time stamped data from three key components: the laser scanner, which measures range and scan angle, a high frequency inertial measurement unit, which records roll, pitch, yaw, and a survey grade GNSS receiver on both the drone as well as on the ground. Then the inertial navigation system calculates range vector using pulse travel time, IMU data, and integrates this with GNSS positioning information. This provides position, velocity, and orientation information of an object relative to a known starting point. This is also known as direct georeferencing. Then in the post-processing software, first the drone GNSS trajectory is corrected using GNSS observations at base station. After that, the corrected drone trajectory is combined with the INS range vector to calculate the precise position and orientation of the sensor for all timestamps. This information is then used to project each laser return into a global coordinate system. So it is analogous to geotagging in photogrammetry, and at the end of this process we get point cloud in a global coordinate system. So if we look at the overall workflow of DSM or DTM generation from drone LiDAR, it looks like this. First, we need to have mission planning. Then through mission planning, we will collect point cloud. After that, we also need to correct the drone trajectory based on the GNSS observation from the base as well as those from the drone. Then this leads to precise georeferencing of the point cloud. After this, the point cloud is processed and noise is removed from that point cloud. After that, the point cloud is classified or filtered into ground as well as non-ground point. So after this, we know which points belong to the ground category and which points belong to non-ground category. Then based on the interpolation of the ground point cloud, a DTM can be generated. Apart from this, a DSM can also be generated. Then these can be used in analysis. For example, calculating contours or also doing cut and fill volume estimations. So let's look at them step by step. So first step is mission planning. The main goal of mission planning is to manage trade-off between point data density and area coverage. So typically in survey, we want to maximize the area that we can cover in a single flight. But industries also have their own requirement of point cloud density. For example, in surveying and mapping, for 1:500 scale map, we need at least 16 points per square meter. Or for example, in power line inspection, where we need very detailed inspection to identify individual power cables, we need at least 100 points per square meter. So there is a trade-off that we need to manage through mission planning between the point cloud density as well as how much area we can cover. So the key planning parameters that control the point density, they are flying height above the ground level. So as flying height increases, the swath width also increases, but at the same time, it inversely impacts the density. Then there is PRF or pulse repetition frequency, which represents outgoing laser pulses per second. So more the PRF, the more will be the point density. There is also scan angle or the field of view, which defines the swath width. There is also flight speed, which inversely impacts point density. So if you have more flight speed, then the point density will decrease. If you have less flight speed, then point density will increase. And finally, we also have side lap, which represents to overlapping adjacent flight lines, which is typically kept at 30% to eliminate gap between neighboring flight lines. This is similar to how we have in photogrammetry as well. Thus, from the efficiency or economic point of view, the aim is to find the largest scan angle at which the minimum point density requirements can still be met. So in a flat terrain, large scan angles may be the best choice. However, in urban areas or in presence of dense vegetation, shadowing effects must be taken into account. Therefore, smaller angles must be chosen here. Additionally, point density also depends upon the ground geometry and the reflectivity of the objects which are present on the ground themselves. So if we look at the key relationship here, so the swath length or L swath is defined as product of the altitude above ground level and twice of tan of half field of view. So we have this full FOV or field of view, then we have here as FOV by 2 this half angle, then we also have the height at which the drone is flying above the ground, so AGL, and based on the tan relationship we can then find out the swath length, half swath length, and then multiply it by 2 to get the full swath length. After we get the swath length, then point density is equal to the LiDAR scan rate or PRF divided by the swath length and divided by the drone speed. So point density is equal to the LiDAR scan rate divided by swath length divided by the drone speed. So in order to better understand this, let's solve a quick question. So what will be the point density of a drone flying with a speed of 5 meter per second at 50 meter above ground level and having a LiDAR which has field of view equal to 90 degree and that LiDAR is firing at a pulse rate of 640,000 points per second. So we can plug in these values in the formulas we just understood. So swath width therefore becomes 50 meter above the ground level multiplied by twice of tan of half field of view. So this gives us 100 meter is the swath width. Then point density is equal to the pulse rate of 640,000 divided by the swath width divided by the velocity, and this gives us a point density of 1280 points per meter square. So a similar setup is used in mission planning softwares. So for drone LiDAR, a common openly available mission planning software is UGCS, and here in this software we have parameters that we can select: the field of view, the flying height, the flight speed. So in this case they are kept at the field of view is 90-degree, flying height is 100 meter, flight speed is 5 meter per second, and also side overlap, which is given here as 30%. We also have option to select which kind of LiDAR sensor we are using. So for this case I have selected DJI Zenmuse L2. Then based on these parameters the mission plan can be generated. So in this case the mission plan has been generated over a selected area of interest. Now the softwares for drone LiDAR data processing, they come either in open source or with commercial license. So in the domain of open source, primarily we have three options. There is Cloud Compare, which is a feature rich tool for editing and registering and analyzing 3D point cloud. It supports lot of features such as segmentation, manual and automated measurement, volume calculation, and change detection. And since it's open source, so more and more plugins get launched every now and often, which can be integrated with the Cloud Compare software. There is also a scriptable data processing library called PDAL, Point Data Abstraction Library, and it is based out of C++ and Python, and it includes filtering, reprojection, transformation, and format conversion. So if we have a batch processing, then the PDAL library is very efficient for that. In addition to this, we have QGIS. Although QGIS in its native form does not support lot of LiDAR data processing, but by downloading plugins of PDAL or LAS tools, then QGIS can also support visualization and basic processing of LiDAR point cloud. And advantage of using QGIS is that it allows integration of the point cloud with other types of spatial, vector and raster data. In the commercial domain, there are several softwares which provide comprehensive data processing, and the advantage is that they support all workflow from end to end. So they support georeferencing, error correction, classification, ground filtering, terrain modeling, and very interestingly in recent years they now support cloud processing. So the whole data set can be uploaded into the cloud and can be processed, and they are also developing more and more AI based feature for different types of object detection or segmentation. And commercial software is also very good at large data set handling. So they are routinely used by survey and mapping professionals. So some of the popular commercial softwares are LiDAR 360, Global Mapper, Pix4D Mapper, AGSoft, Metashape, TerraScan by TerraSolid, and also Trimble Business Center. So once we have acquired the data and we import it into a drone LiDAR processing softwares, first thing we will usually encounter will be noisy point clouds. So what causes these noisy point clouds? So most of the noisy point clouds are either caused by atmospheric scattering, that can be from fog, dust, rain or snow. They are caused by shiny or reflective surfaces like water on a calm lake or glass or metal. They are also caused by low overlap or gaps in coverage. And if you are acquiring point cloud in an urban scene, then there can be object movement of vehicles, or in a forest scene as well, there can be movement of grass or the leaves on the trees. So all these lead to noisy point cloud. Then on the right side in the image also we can see one example of noisy point cloud. So this LiDAR point cloud was collected on a snowy day, and we can see that lot of these point clouds are hovering above the ground, and this is caused by scattering by the snow. So some kind of algorithms are then employed to get rid of these noise. So in this case, the snow was removed, and then after removing of this noise, then noise-free point cloud was obtained. So point cloud therefore needs to be cleaned for visualization clarity and for generating mesh and textured model, as well as for DSM and DTM calculation. And if we have noise, then their interpretation in the CAD and BIM workflows also becomes very difficult. So therefore, it's better to clean the noise in order to perform these applications. So for noise removal, we have several algorithms. One of the popular ones is radial outlier removal algorithm. In this algorithm, noise is removed by identifying points with neighbors fewer than a set threshold within a specific radius. So, if a point is there and it does not have too many neighbors within its radius, then it is more likely to be noise. And this removal, this ROR radial outlier removal algorithm is especially effective where point density is mostly uniform, such as a flat surface. So in this case, noisy points will stand out by having very few close neighbors. So the main parameters we have to define here when we want to implement radial outlier removal algorithm is radius, the search distance around each point, as well as the minimum number of neighbors we want to compare. In addition to this, we have more sophisticated algorithm called statistical outlier removal or SOR algorithm. This algorithm identifies and removes noisy points by calculating average distance of each point to its neighbors. And points further away from their neighbors than a set threshold, they are identified as outliers and those points are removed. And these thresholds are based on the average distance plus a multiple of the global standard deviation. So in the image on the right, we can see that there is a point cloud, but there are also a lot of noisy points which are present. Then these noisy points were removed using the SOR algorithm, and then this relatively noise free point cloud was obtained. So there are two main parameters for the SOR algorithm. First is the number of neighbors, which control the sensitivity to local variation. So if you have higher number of neighbors, then that will capture larger scale feature but may miss out small or sparse outliers. And the second filter parameter is standard deviation multiplier. So this sets a cutoff threshold. So if we have threshold of one standard deviation or one sigma, that means only very closely dense point clouds will be considered. And if we have if we consider a standard deviation of 2, then it is slightly more tolerant. So even if points are slightly further away from each other, even then they will be not considered as noise and they will be included in the main final point cloud. After this, there is also sometimes need for Boresight offset correction. So Boresight offset is an angular misalignment between the IMU and the LiDAR sensor. And since IMU provides the precise orientation in terms of roll, pitch and yaw, which is used for georeferencing, so even small uncorrected offset between the IMU and the LiDAR's scanner, this offset can cause non-overlapping point cloud when same target is acquired from different location. So here we can see the same rooftop as shown in the black line. This rooftop is acquired from two locations, and because of Boresight offset between the IMU and LiDAR scanner, we see that the point clouds do not overlap very well. So we see this kind of gap between the point cloud. This is a Boresight offset error. So drone LiDAR processing software, they can adjust Boresight angles by using optimization algorithm such that it can minimize the misalignment between the overlapping surface. So there is this misalignment between the overlapping surface. In the process of minimizing the misalignment, the software can figure out the corrections which are required in the roll, pitch and yaw to get the correct Boresight offset. So after the Boresight calibration, we get very well aligned point cloud from both the scans. So this will give us a noise free point cloud. So in a noise free point cloud, the DSM is equivalent to the DTM in open areas because essentially they are the same. But in contrast to the DTM, the DSM describes the vegetation cover as well as it can describe upper boundary surface of some man-made objects such as buildings. Due to the difficulty of removing temporal objects on the terrain, the DSM can often also include therefore cards and other objects which are present during the data acquisition. So because the LiDAR data acquisition is also automatic, therefore we also need an automatic method for identification of ground points in the point cloud. So in order to determine the terrain, the point cloud is filtered. That is, the point clouds are classified whether they are ground points or whether they are non-ground points. One of the earliest method to achieve this was a local minimum determination, which meant whichever point has the lowest elevation in a given radius, then that point belongs to the ground. So if we have point cloud that looks like this, then all these points, because they have low elevation, then these points are all belonging to the ground. However, this simple filter does not work very well in hilly terrain. So in hilly terrain, you may have this kind of point cloud. So there's a hill, there's a building, and in such a case, there will be a systematic error. If we just want to rely on the fact that lowest point within a radius is the ground, because that may not always be true. For example, if you look here, that may not always be true. Then to overcome such limitations, morphological filters were proposed. So these are a group of filter algorithms based on the concept of mathematical morphology, which involves either erosion or dilation operation. So closing, which is erosion after dilation, and opening, which is dilation after erosion, they can be used for detecting the maximum surface and the minimum surface respectively. So if we have this point cloud, then in this point cloud, if we perform the closing operation, then by that we can identify the top of the surface, which is equivalent to a DSM. And if we perform opening, which is dilation after erosion, then it can detect the digital terrain model or the ground surface like this. Then after that, segment based filtering algorithm was proposed, in which individual segments are generated by aggregating points with some similar properties using cluster growing techniques. So as long as the properties of the segments are similar within some threshold, then that segment or that cluster keeps on growing. Then these segments are classified by analyzing their topological neighborhood relationships with other segments into bridge, man-made objects or natural objects or maybe ground. So this image here shows first of all the raw point cloud, which shows elevation of different point clouds. Then on the right hand we have the point cloud, which is classified based on the segments into either rooftop or different objects. So basically based on this we can identify which is the ground surface, and other objects, other man-made objects or other objects due to either trees or because of the power lines, they are all classified and segmented separately. So this is also one technique of identifying the ground as well as non-ground point. Then in recent years, cloth simulation filter or CSF is getting more and more popular because it gets very robust results. How this filter works is it inverts the point cloud and simulates a rigid cloth draped over it. So if we have this kind of point cloud, then idea here is to invert this point cloud. Then we get this point cloud and then drape a piece of cloth on top of this point cloud. Then wherever the distance between the cloth and the point cloud is above certain threshold, then all those points are identified as non-ground points, and wherever the cloth touches the inverted point cloud, then all those points are identified as ground points. So for example, these are all ground points. So these are all ground points obtained by cloth simulation filter. So an example of this is presented here. So on the left we have noise removed point cloud. Then the cloth simulation filter was applied on this point cloud data in the cloud compare software, the free and open source software. Then from this we get ground points as well as non-ground points. So we can see those distinctions present here. Let's look at this building over here. So the ground point shows the park which is inside the courtyard of that building. So that park is shown, and the building itself is not shown here. It is shown as an empty space. That building is identified in the non-ground point over here as shown here. Similarly, you can see, you can pause and look at other features which are present in the noise removed point cloud, then the ground point and the non-ground point. Now, after this ground point and non-ground point segregation or filtering has been done, you can still see that the ground points, they have holes. So, there are a lot of holes present here, and these holes need to be interpolated in order to be converted into a DTM. So, to generate a hole free DTM, so first of all the point cloud is converted into a continuous vector surface. To do this, first of all, the discrete point clouds are partitioned into a mesh of non-overlapping triangles, which are also known as triangulated irregular network, or also known as TIN. Then the TIN is generated through Delaunay triangulation, which has the property that no point or no vertex lies inside the circumcircle of any triangle which is present in the TIN. And the Delaunay triangulation uniquely maximizes the minimum interior angle of all triangles in the mesh, therefore avoiding creation of long thin sliver of triangles, ensuring a high quality and geometrically stable surface representation. So, for example, if we have these 3-point clouds, we have two options to convert them into triangles. We can either make triangles like these, or we can either make triangles which look like these. Then, as mentioned in the generation of Delaunay triangles, that the key property that we have to ensure here is that no point should lie inside circumcircle of any triangle. So, if we take circumcircle of this triangle, it may look like this, and circumcircle of this triangle may look like this. So, in this case, it seems the circumcircle does not include any other vertex apart from the 3 vertex for which that circumcircle is being created. However, if we look at the other option, in this, if we create the circumcircle, then we will find that it will be a big circle which will also include this another vertex. So, that means this option, the second option is not a Delaunay triangulation. So, this is how Delaunay triangulation works, and through Delaunay triangulation all the points in the point cloud are converted into a triangulated irregular network. Then this shows an example of gap filling by generating a tin mesh using the Delaunay triangulation. So, on the left side we have the ground points which still have holes. So, you can see the holes are present here. Then through Delaunay triangulation a tin mesh is generated, and then all these holes are filled. So, for example, if we talk about this particular hole, then it gets filled. These holes are also filled over here, and this happens essentially through interpolation, which leads to a DTM generation. Now, this DTM is still in the form of a tin network, and utilizing a tin is not very easy if you have other data sets in form of a raster. So, an additional step is performed where the tin data is rasterized, which is essentially converting the tin data into a raster. And as you know, each raster cell has a single representative value. So, we need to create a raster and provide a single representative value to each grid cell of that raster. So, this is done by superimposing a 2-dimensional grid on the point cloud tin data. And for each point in the cell, a statistical operation, for example, we may want to consider the maximum of all the point, or we may want to consider a minimum of all the point. That kind of statistical operation is performed. So, the primary output through rasterization is either DTM or DSM, where the values assigned to each cell represents its elevation or the Z coordinate. And through rasterization, it creates a continuous surface for analysis. So, this raster data can then be used for slope calculation or aspect calculation, volume calculation, so on. And because it is in a raster format, it simplifies data storage and it facilitates integration with other raster based GIS datasets. So, this is showing the rasterization of tin vector in cloud compare software. So where to create the 2D elevation map, first each point's z height is isolated as scalar field. This gives the raster tool which number it needs for each grid cell. So it is in cloud compare it is known as projection, and then first the point cloud is exported to a scalar field. So, and we are exporting the z value of the scalar field. Then the next step is rasterization of the 10 vector, where as a user we define the grid resolution or the cell size of the raster, which interpolation method to use, and how to handle those empty cells using the interpolation method. Then these values can be given into the cloud compare software, and this kind of rasterized DTM can be generated. So on the left side we have the DSM which is generated after rasterization, and on the right side we have the DTM which is generated after rasterizing. Then these rasterized DTM can also be used for contour generation, or they can, or the DSM can also be used for contour generation. So this shows the contours over the DSM. So we had a building over here and it shows contours of that DSM which are produced at 1 meter interval using the cloud compare software. Then those contour intervals can then be used to calculate volume estimation through cut and fill methods in other softwares also. For example, in reality scan software. So for the same building, the contours are imported into the reality scan software, and the cut volume which is estimated over here is about 54,000 meter cube, and the fill volume which is estimated here is about 8,300 meter cube. So these kind of volume estimations can also be done once we have the contour estimation which is obtained from the DTM and DSM estimation, which are obtained from the 10 vector data which is obtained from the ground and non-ground point cloud data. So these are the overall point cloud classification and product generation. There are ground points, there is off ground points, there is DTM, there is DSM, and also contours which are calculated based on that. Then in terms of application, both DSM and DTM are very valuable. For example, in hydrological modeling, the highly accurate DTMs are very much required for precise floodplain mapping and water flow analysis. In forestry, canopy penetration is very important. So LiDAR is extremely favored over there to map both the top of the canopy in terms of DSM as well as the ground in terms of the DTM. As well as in forestry management, it is important to measure the tree height, canopy density, and estimate the biomass for carbon stock assessment. In precision agriculture also, DSM and DTM derived from the LiDAR data are used for monitoring the crop health, crop height, density, as well as waterlogging zones to optimize irrigation and ground preparation. Recently, they are finding more and more use also in 3D city modeling to create digital twins of urban areas for planning, shadow analysis, or simulating also urban heat or line of sight analysis. So, in summary, we learned about the advantages of drone LiDAR today. We learned about the components of drone LiDAR setup and how they measure the point cloud, the processing required for generating DTM and DSM from the drone point cloud, the noise removal, filtering, as well as rasterization. So, thank you very much for today.